All right, so you've seen the first half of 7.4. We're going to finish the second half today. And we're going to start with example number 6, which looks like this. This question asks about solving using mental math. Whenever you're using mental math, what you need to keep in mind is that I can't see what's going on in your mind. Which means that I understand it says you're using mental math, but you're still going to have to either write me a couple sentences or show me a little bit of what's going on in your brain so that I know what process you're using. Sometimes there's more than one sort of process that makes sense mentally, and I want to see how you're thinking. That way, if there is something that you have a misconception about, we can clear it up. So there's a couple of things that are going on in these problems. A lot of it is hinging on the fact that it's easy to find 10% of a number. So if we looked at the number 15 as a percent, 15% breaks down very nicely into 10 and 5. Agreed? Yeah. So we can take this and we can easily find what 10% of this number is. What is 10% of our number? Yeah, $4.20, right? It's just a matter of moving a decimal point. My 6th graders are still struggling with that idea. Really struggling with the idea of not really needing to do the multiplication. So they keep doing. Stop writing lots of zeros everywhere. The other one, then 5%, you can find quickly by looking at 10%. How? Halving it, right. So 210, right? And then what would we do to find 15%? Yeah, add them together. So this is $6. It was dollars, right? Yeah, $6.30. It's 3 steps. You found a 10%, you divided that 10% by 2, and then you added those two numbers together. About 3 steps is the most you're going to be able to mentally process for most people at one time. If something's taking you more than 3 steps, there's probably something you're not thinking of that's much easier than what you're doing, okay? So try to keep that in mind as you're working through this process. The next one, 20%. What could we do to get 20% easily? Yeah, 10% and add it to itself or double it, right? So what would 10% of 280 be? Yeah, 28. And then you can either think I'm going to double that and multiply by 2, or you can think that you're going to add it together with itself. Either way is fine. And what will be your result? Yes. Okay. So should you be able to do this work in your head? Absolutely you should. But you should also be able to and willing to write down just a couple of statements for me so that I know what you did in your head, okay? All right, let's try another one. 5%, I bet you can do 5%. We already did 5% on one. What would you do for 5%? 10%, which is what? $3.20. And then what? Half it. So 10% divided by 2. So what's half of 320? Yep, 160. Okay, so part D, it's not really meant to be a trick per se, but it is meant to show you that we don't always just double and half things and add them together and so forth. It says 25%. So is it possible that you could do 10%, double it, half it, and then add those 3 things together? Sure. But at that point, you're looking at quite a few steps. Are you with me? You really are. And to process all of that truly without writing anything down and in your head, like mentally, would actually probably take a lot. It's a lot easier on part D to remember that 25% is equivalent to 1/4 or division by 4. Right, that's what 25% is. It's 1/4 of something. I cut it into fourths and I eat 1/4 of the brownie or whatever. So I have my 84, and instead of finding 10% and 10% and 5% and adding it together, I just need to divide by 4. What is 84 divided by 4? What is it? 21. Yep, 21. Any questions on the mental math pieces? Okay. Yes, ma'am.
If it was 75%, how would you do that? Would you just take the 21 and multiply it by 3, or?
That's a good question. You certainly could. It would still just be a two-step process. That's probably what I would do. I probably would do the division first, because making something smaller and then making it bigger keeps numbers more manageable, but making it bigger and then smaller usually gets a little bit harder. So yeah, that's what I would suggest doing if you had 75%. Another thing that you could do is you could find the 21 and then subtract it from the 84. That would be another option.
Okay. Thank you.
All right, let's take a look at a problem C type question. Why is it possible to have an increase of 150% in price, but not a decrease of 150% in price? Emma?
So like if what I don't know, for me it makes sense because you can have like so like if something's like $2, 100% of $2 is 2, and so if you had a 100% increase in before, but sometimes prices increase more than 100%, but they can't so like I can't say, oh, I'm gonna have a 150% decrease, but if there's something for $2, then I'll be looking at negatives. You can't have negative.
Yeah, so we always have the ability to add more to something, right? But when we're talking about a real world context, which this is money, there is a limiting ability to subtract something away. There is a point at which I can't subtract any more away because I have nothing left to subtract. So we'll put something down of that nature. We can decrease only 100% before we have negative numbers. But we can increase as much as we like. Because we are adding to the price. And you're exactly right, Emma. If you were to increase 100%, it would take something that was $2 and make it double, right? $4. So if we increase 150%, we're more than doubling the price of something. So what's really happening? Sometimes there's this misconception of how 150 compares to a 50% increase and how that actually works out. But if you're increasing more than 100%, then you're more than doubling the price of something or the quantity of something. All right, one more component in this section we're going to take a look at is interest. There's only one type of interest we're going to look at. When they redid this book, they eliminated the other ones, so we're just going to do the one that they have. The interest that's in our book is simple interest. So first, a definition for interest. This is the amount of money you pay or earn to borrow or lend money. So if you're borrowing money, then you pay interest back. If you've put your money into a bank or something, then they give you interest, and that's money you earn. Principal is the original amount used to determine interest. So it's either the original amount you put into the bank or the original amount you borrowed from the bank. And I say bank, it doesn't have to be a bank. It could be an individual person or something like that too. Interest rate is the percent used to determine interest. It's actually the R in the problem below. as a decimal. So we want to take the percentage and turn it into a decimal before we actually use it as R. Simple interest has two formulas, but they're not really different. One just has the P distributed through. And so it's P plus PRT or P times 1 plus RT. I already identified that R is their interest rate, right? We also have two others here. P is the principal. Actually, I have that on my screen too, so we'll just put it up here. That's P, my problem below. And the last one is T for time. And the time is always measured in years. So if it gives you a number of months in the problem, you have to make sure to first find the corresponding number of years for that to make sense. What you'll notice is a couple of things. This formula is really intuitive. This is the principal, the amount. Let's just talk about borrowing so that I can stop using my language in both directions. P for the principal, if you made a loan, right? It's the amount you borrowed. The PRT is the simple interest up here that it talks about that you would owe back, the additional amount you would owe for interest. Oh, it's down here. There it is. I equals PRT. So this is the amount that you owe in interest added to the original amount that you borrowed. And A then would be the amount that you have to pay back to pay off the loan. All this is that the P is factored out. So it's in front, and so it's written a little bit differently. It doesn't matter which one you use, just pick which one you like. And of course, on the bottom, it shows you that the simple interest is the portion at the end, I equal PRT. Okay, so let's do an example. A company is expanding its line to include more products. To do so, it borrows $320,000 at 13.5% annual simple interest for a period of 18 months. How much interest will the company be charged? So do you want to use the first one or the second one formula? The first. Okay, so we'll use the first. So our A equals P plus PRT. It actually asks just how much interest is being charged, so we don't actually need the whole formula. We only need the ending part. So let's just do that part, I equals PRT. So the P, the principal, the amount they're borrowing is what? $320,000. The interest rate says 13.5%. So if I have 13.5%, what is that as a decimal? Yeah, 0.135, or you can just write 0.135, either way. So that's my interest rate over here. And then time. How much time? Yeah, 18 months, which is 1.5 years, right? And so good job remembering that we need to put that in terms of years. And then if you will grab your calculator, it will tell you how much interest this would be. What did we get? $64,800 it is. If for some reason as you're working through it you had not sort of picked up on what it was asking for and we used the original equation, right, that I wrote down, that's totally fine. You'll get a number that's different. That number would be the total amount that they owe back, and you could just subtract off the original amount they borrowed to find what it actually is the interest rate. Any questions on that? Okay, we're going to look at a couple more examples, maybe it's two more examples that are related to the ideas of percentages. This first one is, it's like a part C kind of problem, but what it does is it actually analyzes the idea of increasing by a percentage and decreasing by a percentage and asks you the question of does it actually result in the same thing? So because of a recession, the value of a new home depreciated 10% each year for 3 years. That meant it went down in value. Then, for the next 3 years, the economy began to recover and the value of the house increased by 10% per year. Okay, went down 10% 3 times, went up 3%, 10% 3 times. And the question is, did the value of the house increase or decrease after the 6 years? Or another possibility is it could stay the same. It sounds like it stays the same, right? Up 10% 3 times, down 10% 3 times. Why wouldn't it stay the same? Well, that's what we're going to take a look at, is what happens. Now, what you'll notice that you don't know in this problem is how much the house was worth at the beginning, right? Yeah, and the reality is it doesn't matter. You can pick. Just choose something. And then once we choose it, we can just use it for the problem and we compare our answer at the end to what we started with at the beginning. Sound reasonable? And in that vein, I'm going to choose something that's very nice. Year 1, I'm sorry, I should put year 0. Start. At the start. We're going to make the house $100,000 because it's nice to work with. And we get a pick anyway, so we might as well. So at year 1, it goes down 10% in value. So it's worth 90% of what it was the year before. Does that make sense? Okay, so we can actually take 90%, which is 0.9, and we can multiply it by our $100,000 original priced house, and we can find out what it's worth on year 2, or on year 1 after the initial start year. And what do we find? 90,000. That's correct. And we're going to do the same thing for year 2. Year 2, we're going to multiply by 90% again. But it's 90% of the $90,000 value that it currently has at the beginning of year 2, or the beginning of year 2, or the end of year 1. So what is 0.9 times 90,000? Yep, 81,000. And we need to depreciate for one more year. Year 3, 0.9 of 81,000. And what do I have? 72,900. Okay, everybody good at that point? The homeowners are not good at this point. This is bad news, right? They've lost almost $30,000 in the house at this point. Not good. But thankfully, it just describes that on year 4, it's going to go up in value. So now instead of taking 10% away, we're going to add 10% to what we had. So we had 100%, we have 10% more, that's 110%. And 110% would be the decimal 1.10, or you can just write 1.1. That's 110% as a decimal of the $72,900 home. So, what is 72,900 times 1.1? 80,190. Now we're going to repeat this process for 2 more years, for year 5 and year 6, before we can make a comparison. So again, 1.1 of the 80,190. What do we have for year 5? And my last year, year 6, 1.1 times the 88,209. And what do I get? Okay, we'll round to the nearest dollar, so let's go with $97,030. That's the 6 years it represented. Yes, Katie?
Why did you get 1.1 again?
Because 100 plus 10% is 110%. And as a decimal, if the decimal point's here, right, then we would move the decimal 2 to the left. Okay, so let's answer the question on part A because we have enough information now. Did the house increase or decrease in price? Decrease. And what we're going to do on part B is analyze by how much it decreased. I mean, we made up the number 100,000, right? We did. But we can actually take that out of the equation, so to speak, right? Our arbitrary choice by looking at the percentage that it increased or decreased. So let's actually look at the percentage that it increased or decreased. So the original price minus the new price is their decrease, right? So the original price was $100,000 for the particular, scenario that we created, minus the $97,030. So the actual value that they lost on the house was what? Should be $2,970. Is that what you have? The value they lost? Yeah? Nobody's, yes, okay, I got some nods, that's good. Okay, good, 2,970. All right, so what we're wanting to know is what percent that is. So we can take that loss that we had, that 2,970, and we can divide it, we're comparing it rather, to the original cost of our house. That's the $100,000 house. So it's the amount that we lost on the house, or if we had gained, we could have had the amount that we gained on the house, divided by the original price of our house, and we're going to turn it into a percent. So we set it up as a proportion. At least that's one way to do it. We can cross multiply, and we have 100,000 x equals 29,700. So 297,000. And if I divide, this is why the actual amount didn't matter, is because we end up using it again in the problem to find the percent, and it eliminates itself from the actual process. And what do we find? Yeah, 2.97% loss or decrease. So they lost about 3% in the purchase price that they had of their house over that 6 years. Hopefully the next year goes up another 10% and then they're in the black. That would be good. Okay. One more example, and it's COVID. So I think I told you probably day one that I've been tracking COVID numbers since April 1st last year. I've continued to do so for the state of Oklahoma, with the purpose in mind that we could actually use data that's like real data. So we're going to take a look at that. Gracie.
On that one, sorry, just a quick question. When you put 100, was that because your house was $100,000?
To start with, yeah, it was the purchase price we chose. It's the same reason that we subtracted it from 100,000 right here.
Okay.
Is because we're finding our loss based on the problem as we set it up.
Okay.
Yep. So it's worth noting, though, too, Gracie, since you mentioned it, that had we chosen a different price of the house, we would still get 2.97% here on Part B.
Oh, yeah, definitely did not.
Part A would actually be a different number. It would still tell us that it was a decrease, but we still would get 2.97% on a different purchase price. Yeah. All right, so let's take a look at some examples, a problem with a few parts to it about COVID. So I created this in the end of the summer, so my data is already dated. Dated data. All right, as of August 1st, 2020, the total number of positive COVID-19 cases in the state of Oklahoma stood at 37,731. The population of the state of Oklahoma as of July 1st, 2020, because I couldn't find anything closer at the time, was 3,956,971. These are not pretty numbers because they're real, right? We make up really pretty numbers when we make tests and create examples in books. These are real numbers. First question, what percentage of Oklahomans had contracted COVID-19, or maybe it should say had tested positive anyway, as of August 1st? So we're going to do that just like we did really on this last part of this problem. We're going to set it up as a proportion. That's not the only way to do the problem, but it is one option. So we have 37,731 positive cases. We have 3,956,971 people. And our question is how much out of 100% is that? So as we take this problem, we write our 3,956,971 equals, and now I have 3,700,000, oops, not one there, 70, let's see, 773100. So 773,100. And then I would divide by 3,956,971. And what do we get? So grab your calculator because you're not doing that in your head. Say it louder.
0.95.
Fabulous. 0.95%. So that's almost 1, right? Almost 1%. So at that point, if you're only looking at positive test results, which there's a lot of fuzziness with that number anyway, but if you're just looking at the data that's retrievable, which is that's 1% of the population that had contracted it at that point. Part B. At that same time, 10.92% of the positive COVID-19 cases were in kids ages 0 to 17. How many kids does this reflect? So this question's asking you how many kids in the state of Oklahoma, if you will, actually represented that 37,000 number. So we have 10.92. Hang on, let me write it this way so that it matches the one I did before. We have a number of kids out of my 37,731, and that is supposed to be 10.92% out of the 100%. Oops, not 1,100. Okay, so cross multiplying again, I have 100x equals, I'm going to help you out. This is 412,022.52. That's what it is if you multiply it. And if I divide by 100, what does that do to the number? Just moves the decimal, right? So it moves the decimal 1, 2 places to there. So with a little bit of rounding, because otherwise we can't have part of kid. It's generally frowned upon. 4,120 kids. Ages 0 to 17. 4,000 kids had it. At the time, again, another number based on July 1st data, there were 981,328 kids in Oklahoma. Using your answer from Part B, what percentage of children in Oklahoma had tested positive? So our total population had been 1%, right? 1% of the population had tested positive. So this question's asking, well, how does that affect children? Is it also 1% of children, or is there something different? So we have 4,100 children out of the total 981,328 children. And we want to know what percent that is out of 100. And we'll cross multiply. So again, 981,328x equals 4120, a couple more zeros, and we'll divide by the 981,328. And we actually find out that this number is what? 0.42%. Now that's not 42%, that's 0.42%. So that's less than half a percentage. At the very least, by comparison, it's less than the 0.95, right? The general population was 0.95. The children's population, if you will, was 0.42. And just to give you a reference, what this actually means, and we'll talk more about this later in a different section, is this is actually 4 out of 1,000. So every 1,000 kids, you'd find 4. That's the percentage, the ratio that was happening at the time. Fun stats, right? Real life stuff.